gosh.
Jet fuel blend stocks and
Thank you.
hydrocarbon chemicals to mitigate climate change. And if there are any authors, any speakers here who have not signed the media waiver form, I have copies over here. Anyone? Okay, so I'll assume that all the speakers have signed that.
Okay, good morning. Hopefully you can hear me okay. Name is John Hannon. I'm from Vertimass, and Lee Lin, thank you, read out the title of the talk. So first of all, I'll talk about kind of setting the stage here, the need for sustainable hydrocarbon fuels. There's a massive need out there. We're looking at heavy-duty transportation vehicles here, airline consumption, 97 billion gallons per year, 2017, which represents roughly 0.4 terawatts. Terawatts being 1 times 10 to the 12th watts. World diesel consumption, just short of 450 billion gallons per year, representing about 2 terawatts. So that's what's used out there now. The only, and we're shifting gears to down here, the only real impact we've made for biofuels over the past, say, 40 decades has been with ethanol. So with ethanol, the world production is roughly 27 billion gallons per year, but that only represents about 3% of the requirements that are above for heavy-duty vehicles on an energy basis. There are studies out there, the billion-ton study in the U.S., as well as this recent IRENA study, that mentions that the biomass potential is huge out there. So the potential to convert that, if you convert all that biomass into ethanol, you can reach about 90% of the above requirements. However, ethanol, has low energy density, and it doesn't have suitable properties for powering aircraft and heavy-duty engines. So it really almost begs the question, or begs the need for, okay, are there ways to convert ethanol into these other fuels? And so this is where we come along, Vertimass. So we licensed the technology from Oak Ridge National Laboratories that they invented this catalyst that converts ethanol into these heavy-duty fuels. So we call it the consolidated alcohol dehydration and oligomerization process, in short, the CATO process, where you take ethanol, it comes in, it can be hydrous or anhydrous ethanol comes through. We send it through a vapor phase heterogeneous catalysis with low-cost metal exchange zeolite catalysts, and we produce a combination of aromatic and aliphatic hydrocarbons. We call it a blend stock. Currently, the blend is about a C4 through C12 hydrocarbon. You can kind of see how it maps out here on the hydrocarbon. We have a significant amount of aromatics in this, as well as paraffin. So it's a combination. I'll get into this in a little bit more detail. But that's the basics of the technology. And so if you look just schematically, what this now enables is it enables ethanol producers, so existing or new facilities that take in biomass or corn or sugarcane. They ferment it to make their broth and then distill it off. Now the ethanol producer now has the ability to make ethanol if they want to make ethanol, or they have the ability now to run it through our CATO converter to make these different fuels. So you can make gasoline, diesel, jet fuel, as well as this plastic precursor BTEX, benzene, toluene, xylene. There's ethyl benzene in there as well. But these are used typically to make plastics. There's hundreds of uses of these chemicals. But that's in a schematic. That's what this technology now enables. Looking at the mass and energy flows for a kilogram of sugar that kind of goes through this process. You start with a kilogram of sugar, 15.6 megajoules. You run through that's our starting material. You run through a fermentation process. In that fermentation process, you make ethanol. About half it goes to ethanol, and you see how the energy is conserved, more or less. You also make, the other half is about carbon dioxide, but that's a non-combustible material. There's no calorific value there. And from this ethanol, you send it into our catalytic reactor. You maintain the majority of the energy. The energy gets transformed into these hydrocarbon products. And then you also produce water. So again, no calorific value there, but you can see on a mass basis about 40% of what goes in. Overall energy is about 94% conservation across this process. So I'll talk a little bit about some of the technical advantages of this technology, as well as some of the commercial advantages. So some of the technical advantages are It's a single cell, it's a single reaction system, okay? We've seen attempts at alcohol to jet or alcohol to hydrocarbons in the past, and these have typically been 3 to 4 step processes. We also have complete conversion of ethanol. All the ethanol converts into hydrocarbons and water. We operate near or ambient pressure, so just enough to drive it through the bed, versus previous attempts where they're a few hundred psi. Relatively moderate temperatures. The other important thing is there's no need for external hydrogen, and then finally, it's a very low CapEx, OpEx solution. So these cellulosic ethanol has had challenges in the past, as Lee presented, these $10 per installed gallon, or north of $10 per installed gallon. This is about a fraction of that to give the cellulosic ethanol producer the flexibility to make these other products. So it's a low CapEx solution. So on the commercial advantages, we find in talking to ethanol producers out there today is that this technology can actually in a lot of the plants, de-bottleneck it. So a lot of these plants have bottlenecks at the distillation or rectification column. This allows them to de-bottleneck and actually make more product overall. It's fungible, to go to Buzz's, your comment about the ethanol not being able to go into the pipelines, where this can, because this is now a hydrocarbon product. As I mentioned, it preserves most of the energy content of the ethanol that is sent in. And then the other interesting piece here I'll get into in a bit is this technology can be scaled up commercially from the current demonstration reactor. So I mentioned we license this from Oak Ridge National Labs. It's a 1-step versus 3 to 4 for others. Very positive freedom to operate. We licensed 5 initial patents back in 2014. On top of that, we've added 5 more. 1 has been recently issued. We have 4 more kind of under review. And then we have some funding support from the Department of Energy, BETO office, as well as the ChemCat Bio program, which allows us to really characterize a catalyst with all the sophisticated tools across the national labs. So that's Vertimass. One nice thing we love about this is that we really can launch from a solid platform that's out there already. So in the United States, about 220 ethanol plants producing about 15 billion gallons per year. There's only a couple cellulosic ethanol producers in this mix, but it's predominantly first generation or starch ethanol production. And then in Brazil, we get about 6 billion gallons total from 126 plants, and you can see how they're kind of scattered about. But this really gives us a nice platform to launch from, to start integrating our bolt-on onto these facilities to start making these renewable hydrocarbon products. When we started, when we were awarded the Department of Energy award, we looked around for companies that could help us scale up this technology, and Technip FMC was right on the list. They're actually just around here in the Boston area. What we really liked about them is they've got about 4 decades of experience scaling up catalytic technologies like this in the past. They've commercialized 20 processes from this laboratory that we're working with now. So they have great success rate, and they also have the capabilities of large engineering firms. So they can provide engineering, procurement, and construction, or EPC packages. And the other neat thing that we really liked about this is they're able to scale up commercially directly from this demonstration reactor that we're working with. So they can guarantee this scale up. So that's a big game changer, because typically in other processes you'd have to have a unit that's installed in the field, and that's usually bleeds you of finances. So being able to go directly to commercial is huge. Through this Department of Energy grant, we took a number over the past 2 years. Here, this is a graph that kind of encapsulates the progress that we made over the past 2 years. Again, axis about roughly 24 months. On the y-axis, you see liquid hydrocarbon yield. And so this is an important parameter. This technology, again, as I mentioned, makes hydrocarbons, and it makes water. The key with the hydrocarbons is you want to maximize the amount of liquid hydrocarbons you make versus gaseous hydrocarbons, because the liquid hydrocarbons command about a 4 to 5 times value than the gaseous hydrocarbons. So the real goal in your techno-economics is to boost the liquid hydrocarbon yield. Okay, we call it C5+, meaning hydrocarbons that are liquid at ambient temperature and pressure. So when we started off, we had the technology that could produce about 36% liquid hydrocarbons on laboratory powder at a very small scale. We transferred that technology to Technip, and over time we started off low, but then we were able to catch up to the 36%, and from there we were able to increase the liquid hydrocarbon yield over time. We've moved from laboratory powdered pellets to pilot pellets, and that's mainly the bigger you get, the less you can use powdered catalysts because the pressure drop's just significant. And then over time, we moved to commercial extrudates, and we were able to keep our hydrocarbon liquid yields just above 80%, so roughly 85%. Our target's 90%. In the same time, over those 24 months, we were able to also decrease the catalyst costs. So this is kind of the purple color, purple dash line, starting at about $600 per kilogram, and over time we were able to drop that to about $70 per kilogram. So it's about a 10x decrease in catalyst price. And then finally, the scale of development as well. This is a kind of dashed black line where we started off at scale X or 1x, and we increased that to about 300x. So we did a lot over those past 2 years by increasing the liquid hydrocarbon yield, decreasing the catalyst costs, and increasing the scale up. So that's kind of the development work we've done. Here's one of our reactors. Okay, so I'll cover this a little bit quickly here. So 2 graphs here just to kind of show you the type of products that we have, the Cato reactor products. On the left here, this is an example of hours on stream of operation. Okay, so this is 0 to 70 hours. The dashed vertical lines represent the regeneration times, and then you can kind of see how the product distributions look. This is liquid hydrocarbon yields. This piece here, kind of green dots are the BTEX yields, and then we look at methane and the whole bunch of different other products that are in there that I'm not showing. And then, if you do take a sample of this C5+ liquid, this is what the profile typically looks like, going from a C4 hydrocarbon to C12, and it's broken down by color here, aromatics being the predominant one in blue, is followed by aliphatics and olefins. So that gives you an idea of the breakdown of the liquid. The other thing we did was, in this recent study, was look at 2 things, and Lee alluded to this during his presentation, but if you look at this complete top box, this is the ethanol production process. You get your process up front, and this is more the downstream processing where it goes through a beer column, rectification, molecular sieves, and you get your 100% ethanol product. That's BAU, business as usual. This bottom piece here is, okay, how would we integrate our Cato bolt-on into this system? We have kind of 2 blocks shown here with some heat exchangers, a reactor decanter, and we make our fungible fuel blend stocks. And this is how we see it kind of integrating, some little bit of heat integration. And then we look at a feedstock of 40% ethanol, which is typically what you'd see off a beer column vapor. Those are the kind of 2 scenarios. So we're looking at 100% ethanol and comparing that to how much it costs to make fungible fuels. And what we found is, looking at the y-axis here, when we started off, it was about $24 per gigajoule. And just to give you a sense, it's about $1.25, $1.25 per gallon for just the conversion process. When we started off the technology, over the development process, we were able to take that down in about 2 years to about 1/10 of that. So we're down at about $2 per gigajoule, or just about 10 cents per gallon for the conversion process. We project that we're going to be able to get even lower, to about $1.45. And as Lee mentioned, this is very important because to take 40% ethanol and to convert that to 100% ethanol requires $1.46 per gigajoule, where we're currently at 2, targeting 144. So what we're saying is that there's the same amount of cost to take 40% ethanol to anhydrous ethanol. It's the same as taking that 40% ethanol and convert it to hydrocarbons. So this kind of just shows you here, same thing, 146 for this conversion process here. Now we're at $2 now for this conversion, taking that 40% ethanol and upgrading it, and 144 projected. And the key here is the ethanol is now not really a product, it's an intermediate. So think of it in that sense. The other thing we looked at was, okay, so you can do this, how competitive is it with petroleum-based hydrocarbons? And so we've done a lot of numbers here, but I'll just cut to the chase. If you compare it to petroleum, which these are in dollars per liter, so 0.48 at a $60 per barrel oil and a $0.8 per liter at 100 per barrel oil, what we find is that these technologies, almost all these technologies compete at $100 per barrel oil without any incentives. It's very challenging though. None of them compete at $60 per barrel without incentives. Now talk about incentives. There are incentives out there. On the left is really the incentives that exist. So you got D3 RINs for cellulosic ethanol, you got D5 RINs for sugarcane ethanol, and D6 RINs for corn ethanol. And there's also the California Low Carbon Fuel Standard. That these are current incentives that are out there. And then there's other incentives that may be coming down the line. So we have a $100 per ton CO2 incentive that we looked at, as well as this kind of oil industry shadow price where they look at $40 per ton CO2. So we say, okay, how competitive is it if we incorporate the incentives? And again, a lot involved here, but what we do is we look at the different technologies, cornstarch, sugarcane, and then the cellulosics down below here. We look at how competitive they are with $60 per barrel oil, $80 per barrel oil, and 100 with payback periods. So, you know, if it costs you X capital, how quickly can you pay back that capital with these different incentives? And what we find is that $60 per barrel oil, there are a few of these technologies that will fit. The corn ethanol with LCFS, as well as some of the sugar canes will have payback periods. And then as you increase the oil price, you start to see more bars and more payback periods, and certainly under $100 per barrel, you start to see real fast paybacks, less than a year for some of these technologies. You can't really see it, but we also have a break-even oil price ranging from about 40 to 120. So the other thing we look at, you know, all these prices are changing all the time: gasoline, diesel, jet fuel prices, as well as ethanol and certainly corn. These prices change over time. So we say, okay, if we do a look back, okay, say over a 5-year time period, if the ethanol producer had this technology, would they be able to make money with it? And what we find is that yes, there are these windows of opportunity highlighted here in the kind of greenish color, where if they do operate the bolt-on there, their margins just skyrocket. So you can see huge margin increases, 30, 40% for these different opportunity zones. So our thinking in the future is, you know, once we start bolting on to their facilities, it gives them the ability to make these hydrocarbon products if it makes sense, financial sense, or make the ethanol if it makes sense, or combinations of the two. This last segment here talks about, we talked about the economics, and the last segment is about the life cycle analysis. So we work with Argonne National Labs to look at how the greenhouse gas emissions look, and this is kind of just a schematic of the flows. And what we find is, for first generation greenhouse gas reductions, for corn starch and cane sugar, offer 40 to 69% greenhouse gas reductions. Moving to second generation production ranges from 70 to 96%. So really good looking greenhouse gas reductions. And this is my final slide, just kind of a recap, kind of take home messages, is that, you know, this technology allows ethanol producers now to make gasoline, diesel, and jet fuel and higher chemicals without adding hydrogen. It's a low CapEx, OpEx solution. As I mentioned, the greenhouse gas reduction incentives set 40 to 70% roughly for first generation and 70 to 96% for second generation. And the other interesting piece of that paper was, you know, you can produce hydrocarbon fuels now at the same cost as removing water from ethanol. These technologies can compete with oil prices, especially with the incentives. And then we're really close to commercialization. I mean, we've done this now for just over 24 months for the study. And so we're really close, about 4 or 5 months before we're ready to commercialize. And then the potential here is huge. Potential for 1.5 plus terawatt impacts in the future. So that's all I have. Thank you so much for listening.
We have time for a couple of questions.
Thank you. Thanks so much for that talk. That's really, you know, promising. For this to have an impact on carbon, it would have to be coupled with basically enhanced, inputs. And I think we all see that if this is based on corn, then is there also a plan or is there some future for increasing the production of corn? And if it's not basically based on corn, do you have a bolt-on plan for cellulosics?
Yeah, no, that's a great question. So we looked at all the feedstocks, right? So we looked at corn, we looked at sugar cane, and then we looked at the cellulosic feedstock from bagasse and then also from corn stover. So we looked at all those scenarios. However, out there in industry now, our feedback is, 95+% of it is corn production in the U.S., and then all of it is sugarcane in Brazil. And so that will likely be our first feedstock that will get into the, get our first bolt-on on. But that being said, I mean, once we optimize the bolt-on in industry at scale, that can be applied directly to cellulosic ethanol production as it comes along. But if we find that the first generation producers have better financial positions now than cellulosic ethanol producers and have more kind of ability to put this on first. Yeah. But our target is cellulosic ethanol as the intermediate molecule. Yep.
Thank you for the presentation. I think it's quite promising, interesting. Actually, I have a technical question. What do you do with the methane, which is a reasonably big amount, at like 10%? And you have also VTX, which is like 20%.
Yeah.
I have seen the flow sheet, but without indication and without temperature. So, and my other question is more commercial. There are other options because this is a big problem, and companies like Abengoa and so on have tried to do in a very big way because of the problem of the prices, as you have indicated. And there are other options, like, for example, producing other chemicals like butadiene or a big effort in how your technology competes with that, because you have shown that there is a window for feasibility comparing with during the prices of the bioethanol, but you have not compared with other competitions. And that is a very key point as well.
Yeah. So
Questions? Keep the answer short, please, so we can stay on schedule.
Anyway, we can discuss later.
Follow up later, but go ahead, John.
Okay, yeah, so the methane, what we do with that is we use it to energize the system, so provide some of the heat, and then we take that methane and also replace what they would normally use as natural gas that they pull into the plant. And then regarding the competition, we have a lot of analysis on that, so I can share that with you, yeah.
Buzz, quick question.
Oh my gosh. I wasn't even expecting to ask it. Could you use the Cato catalyst for carbon capture and sequestration? Could you turn ethanol into some sort of non-volatile plastic with it?
It's possible. We haven't focused on it, but it's definitely possible. We've kind of brushed around the corner, but we haven't gone after it. But yeah, definitely possible.
I'll catch up with you about that later.
Okay.
Okay, let's give John another hand.
Thank you.
Autism. Graph similarity drives OSDA 3 zeolite transformations. You got that up very quickly. Am I pronouncing OSDA correctly? Do you call it OSDA?
OSDA.